In the summer of 1940, as Messerschmitt fighters tore through British skies and Luftwaffe radar stations tracked every RAF sortie with unnerving precision, a quiet chemist named Geoffrey Whitmore stood in a Manchester laboratory holding a tin of paint that would rewrite the rules of aerial warfare. The formula, a peculiar blend of carbon particles, synthetic rubber, and iron oxide, looked utterly unremarkable. Yet, when applied to aircraft fuselages, it rendered them nearly invisible to the very technology Hermann Göring believed would guarantee German air supremacy. What the Reichsmarschall didn't know was that his own scientists had dismissed the possibility of such a material 3 years earlier. By the time German intelligence finally understood what the British had achieved, it was already too late. The ghost Spitfires were hunting. The problem first revealed itself not in the skies over Britain, but in the cold analysis rooms of RAF Fighter Command at Bentley Priory, where Air Chief Marshal Hugh Dowding studied loss reports with mounting alarm in early 1940. The statistics were damning. British fighters were being intercepted with uncanny accuracy before they could reach their targets over occupied Europe. German radar stations along the French coast, particularly the imposing Freya and Würzburg installations, were detecting RAF formations at ranges exceeding 120 kilometers, giving Luftwaffe controllers ample time to vector their fighters into perfect ambush positions. Squadron leader James Hartley, a former Cambridge physicist now serving in the RAF's Operational Research Section, had spent 3 months correlating mission reports with known German radar positions. His conclusion, delivered to a skeptical audience of senior officers in a Whitehall briefing room on a gray February morning, was stark. Gentlemen, we are fighting a war in which the enemy can see us coming from the moment we cross the Channel, whilst we are operating half-blind. Our aircraft are, in effect, announcing their presence to every German radar operator from Calais to Cherbourg. The strategic implications were catastrophic. Britain's ability to conduct offensive operations over the continent, already limited by the Luftwaffe's numerical superiority, was being further constrained by this fundamental asymmetry. Bomber Command's losses were approaching unsustainable levels. Fighter sweeps intended to draw out German interceptors were instead walking into carefully prepared traps. The Air Ministry's plans for a sustained air campaign against German industrial targets seemed increasingly fantastical when every raid was met by swarms of Bf-109s positioned with mathematical precision. What made the situation particularly galling was that British scientists had pioneered radar technology. The chain home stations that had helped win the Battle of Britain were a source of national pride. Yet the Germans had not only matched British radar capabilities, they had, in some respects, exceeded them. Their Würzburg fire control radars could track individual aircraft with remarkable accuracy, feeding targeting data directly to anti-aircraft batteries. The Freya early warning systems could detect formations at extreme ranges, and unlike the static British chain home network, German radar units were mobile, making them difficult to locate and destroy. In the laboratories of the Telecommunications Research Establishment at Worthmut Travers, Dr. Robert Watson-Watt, the father of British radar, convened an urgent meeting of his senior researchers. The question posed was deceptively simple. If radar worked by bouncing radio waves off metal objects, could those reflections somehow be reduced? The initial responses were discouraging. Aircraft were large metal structures specifically designed to be strong and rigid. Making them invisible to radar seemed to violate basic physics, but one voice offered a different perspective. Geoffrey Whitmore, a 34-year-old industrial chemist who had been seconded to the TRE from Imperial Chemical Industries, suggested an approach that seemed almost absurdly simple. We can't change the aircraft's shape or structure without compromising its performance, but we can change what covers that structure. Paint, gentlemen, specially formulated paint. The idea was met with polite skepticism. Paint was for aesthetics and corrosion protection, not for defeating enemy radar. Yet Whitmore persisted, explaining the theoretical basis. Certain materials could absorb radio waves rather than reflecting them. If a coating could be developed with the right electrical properties, specifically the right balance of conductivity and magnetic permeability, it might significantly reduce an aircraft's radar cross-section. The concept wasn't entirely new. German scientists at Telefunken had explored similar ideas in 1937, but had concluded that any material capable of absorbing radar waves would be too heavy for practical use on aircraft. British intelligence, courtesy of reports from agents in occupied Europe, was aware of this German research and its negative conclusions. This knowledge, paradoxically, became a source of hope. If the Germans believed it couldn't be done, they wouldn't be looking for it. Whitmore's background made him uniquely suited to the challenge. Before the war, he had worked on industrial coatings for the automotive industry, developing paints that could withstand extreme temperatures and chemical exposure. He understood the complex chemistry of polymers, pigments, and additives. More importantly, he possessed the practical mindset of an industrial chemist, someone accustomed to making things work in factories, not just in laboratories. The Air Ministry, desperate for any advantage, authorized a small research program in March 1940. Whitmore was given a team of 6 researchers, a modest budget, and access to a small wind tunnel facility at Farnborough for testing. The objective was clear but daunting: develop a coating that could reduce radar reflections by at least 50%, weigh no more than standard aircraft paint, withstand the rigors of combat flying, and be manufacturable in quantity using Britain's strained industrial resources. The theoretical foundation rested on the principle of impedance matching. Radar waves encountering a metal surface experienced a sharp impedance discontinuity, causing most of the energy to reflect back to the receiver. But if a material with intermediate electrical properties could be placed between the air and the metal, a material that gradually transitioned the impedance, much of the radar energy could be absorbed rather than reflected. The challenge was finding materials with the right properties that could be incorporated into a practical paint formula. Whitmore began with carbon. Finely divided carbon black had interesting electrical properties. It was somewhat conductive, but not highly so. When dispersed in the right concentration within a polymer matrix, it might provide the impedance matching needed. But carbon alone wasn't sufficient. The paint also needed magnetic properties to absorb the magnetic component of electromagnetic waves. For this, Whitmore turned to iron oxide, specifically a form called magnetite that exhibited ferromagnetic behavior. The early experiments were conducted in a cramped laboratory in a requisitioned textile mill outside Manchester, chosen because it was far from likely bombing targets. Whitmore and his team worked through the spring of 1940, mixing countless formulations, testing their electrical properties, and trying to balance the competing requirements of radar absorption, weight, durability, and manufacturability. The work was tedious and often frustrating. Formulations that showed promise in electrical tests proved too brittle when dried. Others were too heavy or didn't adhere properly to aluminium surfaces. By May 1940, as German forces swept through France and the strategic situation deteriorated catastrophically, Whitmore had achieved a breakthrough. His Formula 73, a mixture of carbon black, magnetite particles, synthetic rubber binder, and several proprietary additives, showed remarkable radar-absorbing properties in laboratory tests. When applied to metal test panels and measured in a makeshift radar range, it reduced reflections by approximately 65% at the frequencies used by German Freya radars. The news reached Dowding's desk on June 3rd, the same day the Dunkirk evacuation concluded. The timing seemed almost providential. Britain now stood alone, and the Luftwaffe was preparing for an air campaign that would determine the nation's survival. Any advantage, however marginal, would prove decisive. Dowding immediately authorized full-scale trials on actual aircraft. The first Spitfire to receive the experimental coating, serial number K9795, was painted at Farnborough on June 15th. The process took 2 days, as the paint had to be applied in multiple thin layers to achieve the required thickness without adding excessive weight. The result was visually distinctive. A matte dark gray finish seemed to absorb light as well as radar waves. Ground crew nicknamed it the Ghost. Flight trials began immediately. The coated Spitfire performed normally. The paint added approximately 18 pounds to the aircraft's weight, well within acceptable limits. But the real test would come when it was flown past British radar stations to measure its detectability. On June 22nd, Flight Lieutenant Peter Townsend flew K-9795 on a carefully planned route past 3 chain home stations at various altitudes and ranges. The results exceeded expectations. At ranges where an uncoated Spitfire would produce a strong, clear radar return, the ghost aircraft was barely detectable. At certain angles and distances, it disappeared from radar screens entirely. The radar operators, not informed of the test's purpose, reported intermittent contact and possible equipment malfunction. When they were told they had been tracking a single Spitfire, their disbelief was palpable. Whitmore's paint worked. The question now was whether it could be produced in sufficient quantities, applied to operational aircraft, and deployed before the coming battle, and whether, when German radar operators began losing track of British fighters, they would understand what had happened, or simply assume their equipment was failing. In a secure conference room in Whitehall, as summer sunlight filtered through sandbag-protected windows, a decision was made that would remain classified for 30 years. The Ghost Spitfire program would proceed immediately, with absolute secrecy. Not even most RAF pilots would know why their aircraft were being repainted. The advantage of invisibility was too precious to risk through careless talk. Geoffrey Whitmore, the quiet chemist from Manchester, had given Britain a weapon that might help even the odds in the desperate struggle ahead. But transforming a laboratory success into an operational capability would require overcoming obstacles that had nothing to do with chemistry and everything to do with the brutal realities of industrial production in a nation under siege. The challenge of mass-producing Whitmore's radar-absorbing paint revealed itself within days of the successful trials. Britain's chemical industry, already stretched to breaking point producing explosives, synthetic rubber, and countless other war materials, would somehow need to manufacture thousands of gallons of a complex, multi-component coating using ingredients that were themselves in short supply. The task fell to a hastily assembled team that included Whitmore, production engineers from ICI, and a formidable Ministry of Supply official named Margaret Thornton, whose reputation for cutting through bureaucratic obstacles was legendary in Whitehall. The first production facility was established in a converted dye works in Huddersfield, chosen for its existing chemical processing equipment and its location in northern England, relatively safe from Luftwaffe bombing. The site, designated Factory 7 in official documents, but known to its workers simply as the Paint Shop, began operations in early July 1940. Security was extraordinary. Workers were told they were producing a new type of anti-corrosion coating for naval vessels. The true purpose was known only to a handful of senior personnel who had signed the Official Secrets Act under circumstances that left no doubt about the consequences of disclosure. The production process was fiendishly complex. The carbon black had to be milled to a precise particle size. Too large and it wouldn't disperse properly, too small and it would agglomerate into useless clumps. The magnetite required careful preparation to ensure the correct crystalline structure. The synthetic rubber binder, already scarce due to the loss of natural rubber supplies from Malaya, had to be formulated to remain flexible across a wide temperature range while providing strong adhesion to aluminum alloys. And all these components had to be mixed in exact proportions, with the consistency monitored constantly to ensure batch-to-batch uniformity. Margaret Thornton attacked the supply problems with characteristic determination. Carbon black was diverted from tire production, justified by a fictitious urgent admiralty requirement. Magnetite was sourced from iron ore processing facilities in Cumberland, where it had previously been treated as waste material. The synthetic rubber came from a new plant in Grangemouth, Scotland, which had been built specifically to reduce Britain's dependence on imported materials. Each supply chain was carefully compartmentalized so that no single supplier understood the final application. The human element proved as challenging as the chemistry. The factory operated around the clock in 3 shifts, staffed largely by women, many of them former textile workers whose mills had closed or converted to parachute production. They worked in conditions that were uncomfortable and sometimes hazardous. The carbon black created a fine dust that infiltrated everything, turning skin and clothing gray. The solvents used in the paint formulation produced headaches and nausea until better ventilation was installed. And the work was monotonous, endless hours of mixing, testing, and filling containers under the harsh glare of electric lights. Yet the workers of Factory 7 displayed the same stoic determination that characterized Britain's home front. They worked through air raid warnings, though Huddersfield was rarely targeted. They maintained production despite shortages of everything from mixing paddles to storage drums. And they kept the secret even from their families, though the gray dust that clung to their hair and clothes prompted endless questions about what exactly they were making. By late July, Factory 7 was producing approximately 200 gallons of radar-absorbing paint per day, enough to coat about 10 aircraft, but the RAF needed hundreds of fighters treated and quickly. The Battle of Britain was intensifying, and while the Ghost Spitfire program remained experimental, pressure was mounting to deploy the technology operationally. Whitmore and Thornton worked frantically to increase production, but they were constrained by equipment capacity, raw material supplies, and the simple fact that rushing the process risked producing substandard batches. The application process presented its own difficulties. Standard RAF painting procedures were inadequate for Whitmore's formula. The paint had to be applied in multiple thin coats with precise drying times between layers. The surface preparation was critical. Any contamination or oxidation would compromise adhesion and effectiveness, and the work had to be done in controlled conditions, which meant requisitioning hangar space at a time when every square foot was needed for maintenance and repairs. A specialized application facility was established at RAF Henlow in Bedfordshire. A team of civilian painters, recruited from the automotive industry and trained personally by Whitmore, worked under the supervision of RAF ground crew. Each aircraft took approximately 48 hours to coat completely, far longer than a standard paint job. The Spitfires arrived in bare metal, or with their existing camouflage stripped away, were meticulously prepared, coated with the dark gray radar-absorbing paint, and then returned to their squadrons with strict instructions about maintenance and care. The pilots who received these aircraft were told only that they were flying special reconnaissance variants with experimental coatings designed to reduce visibility. Most assumed this meant some form of visual camouflage. They noticed the unusual matte finish and the slightly different handling characteristics. The added weight, though minimal, was perceptible to experienced pilots. Some complained that the dark gray made the aircraft more visible against clouds. Others appreciated that it seemed to reduce glare from the sun. None suspected the true purpose. Flight Lieutenant David Crook of 609 Squadron was among the first operational pilots to fly a Ghost Spitfire. In his diary entry for August 12, 1940, he wrote, "Collected the new kite today. Odd color, very dark gray, almost charcoal. Chaps are calling it the Undertaker's Special. Flies well enough, though she feels a touch heavier in the turns. Told it's some boffin's idea about camouflage. Seems a lot of fuss over paint, but who am I to question the wisdom of the Air Ministry?" What Crook didn't know was that his Undertaker's Special had just become part of a carefully orchestrated experiment. A flight of 4 Ghost Spitfires from 609 Squadron was being tracked by British radar stations during routine patrols, with their detectability compared to standard aircraft. The results were promising but inconsistent. At certain angles and altitudes, the coated aircraft were significantly harder to detect. At others, the advantage was marginal. The radar-absorbing properties were highly dependent on the aspect angle, the direction from which the radar waves struck the aircraft. Whitmore had anticipated this limitation. Radar cross-section was a complex function of shape, size, and surface properties. His paint could reduce reflections, but it couldn't eliminate them entirely, especially when radar waves struck large, flat surfaces, like wings at perpendicular angles. The Ghost Spitfires were stealthier, not invisible. But in the chaotic environment of air combat, where radar operators were tracking dozens of contacts simultaneously. Even a modest reduction in detectability could mean the difference between being intercepted and reaching the target. The real test would come when Ghost Spitfires operated over occupied Europe, where German radar stations would be trying to detect them. Planning for such missions began in late August, coordinated by Fighter Command's Intelligence Section. The objective was to determine whether German radar operators would notice anything unusual about certain British aircraft, and if so, how they would respond. But before these operational trials could begin, disaster nearly ended the program. On the night of August 24th, a Luftwaffe bomber, lost and jettisoning its load before returning to France, dropped a stick of bombs across Huddersfield. One struck a warehouse 200 yards from Factory 7. The blast shattered windows and knocked out electrical power. More seriously, it ignited a storage tank containing the solvent used in paint production. The resulting fire threatened to spread to the main production building, where thousands of gallons of flammable materials were stored. The factory's fire watch team, composed of off-duty workers and local Home Guard members, fought the blaze for 3 hours before fire brigades from surrounding towns could arrive. Margaret Thornton, who had been working late in her office, personally directed the effort to move drums of paint and raw materials away from the flames. By dawn, the fire was extinguished, but the damage was severe. The warehouse was destroyed, along with a week's worth of finished paint. The electrical system was wrecked. Production would be halted for at least 10 days. Thornton's response was characteristic. By midday on the 25th, she had requisitioned electrical equipment from 3 other factories, arranged for temporary generators to be delivered from Manchester, and secured emergency supplies of solvents from a facility in Liverpool. Workers arriving for the evening shift found her still there, covered in soot, directing repairs with the same brisk efficiency she brought to supply negotiations. When someone suggested she should rest, her reply became legendary among the Factory 7 staff. Rest? Hitler doesn't rest, and neither shall we. Now, let's get back to work. Production resumed on September 2nd, running at reduced capacity but operational. The near disaster had paradoxically strengthened the program. The workers now knew their product was important enough to warrant extraordinary recovery efforts. Security was tightened further, and the Ministry of Supply, recognizing the vulnerability of a single production site, authorized the establishment of 2 additional facilities, one in Wales and another in Scotland, to distribute the risk. By mid-September, as the Battle of Britain reached its climax, approximately 80 Spitfires had been coated with Whitmore's paint. They were distributed among several squadrons mixed with standard aircraft to avoid creating an obvious pattern. The Ghost Spitfires flew the same missions as their conventional counterparts: defensive patrols, bomber escorts, and increasingly offensive sweeps over France. And in the radar stations along the French coast, German operators began reporting anomalies. Certain British formations seemed to fade in and out of detection. Contact would be established, then lost and regained. Equipment checks revealed no faults. The operators, trained to trust their instruments, began to doubt their own competence. Reports filtered up through the Luftwaffe's intelligence network, but in the chaos of the ongoing air battle, they were filed away as minor curiosities: equipment glitches, operator error, atmospheric interference. The British, monitoring German radio traffic through ultra-intercepts and other intelligence sources, watched these reports with intense interest. The Ghost Spitfires were having an effect. The question now was how long it would take the Germans to understand what was happening, and what they would do when they finally realized that the British had achieved something their own scientists had declared impossible. In his laboratory office at the Huddersfield facility, Geoffrey Whitmore studied production reports and test data, making continuous small improvements to the formula. He had given Britain a technological edge, but he understood that such advantages were temporary. The Germans were skilled and resourceful. Eventually, they would capture a Ghost Spitfire, analyze the coding, and develop countermeasures. The race was on to exploit the advantage while it lasted, and to stay ahead of the inevitable German response. The first indication that something was amiss reached Oberst Wolfgang Martini head of the Luftwaffe's Signals Intelligence Service in late September 1940. A routine intelligence summary from Luftflotte 3, responsible for operations over the Channel and southern England, included a curious footnote. Radar operators at several Freya stations along the Normandy coast were reporting intermittent tracking difficulties with certain British fighter formations. The contacts would appear at expected ranges, then fade to barely detectable levels, then strengthen again, all without corresponding changes in altitude or course that might explain the variation. Martini, a meticulous officer who had overseen the development of Germany's radar network, initially dismissed the reports as operator inexperience or equipment degradation. The Freya radars, while generally reliable, were complex systems operating in harsh coastal environments. Salt air, moisture, and the constant vibration from nearby anti-aircraft guns could all affect performance. He ordered technical inspections of the affected stations and additional training for the operators. But the reports continued. By mid-October, similar anomalies were being noted at Würzburg fire control radar sites. These were more sophisticated systems, operated by highly trained personnel, and their reports were more detailed and troubling. British fighters, identified as Spitfires by their characteristic radar signatures, were exhibiting radar cross-sections that varied dramatically and unpredictably. At times, they appeared as strong contacts, clearly defined on the display screens. At other times, the same aircraft would fade to ghost-like traces that were difficult to distinguish from atmospheric clutter. What made the phenomenon particularly puzzling was its selectivity. Not all British aircraft exhibited this behavior, only certain ones, and not consistently. A formation of 4 Spitfires might include 2 that tracked normally and 2 that faded in and out. The pattern seemed random, which argued against equipment malfunction. If the radars were failing, they would fail consistently, not selectively. In early November, Martini convened a meeting at Luftwaffe headquarters in Berlin with the senior radar engineers from Telefunken and GEMA, the companies that manufactured Germany's radar systems. The engineers reviewed the operational reports with growing puzzlement. The described behavior didn't match any known radar phenomenon. Atmospheric ducting could cause unusual propagation effects, but not with this pattern. Electronic countermeasures, deliberate jamming, would produce different signatures, and the British were not known to be using airborne jamming equipment. Dr. Hans Plendl, Telefunken's chief radar scientist, offered a hypothesis that was received with skepticism. Could the British have developed some form of radar-absorbing material? The idea was immediately challenged. German research into such materials, conducted in 1937–38, had concluded that any substance capable of significantly absorbing radar waves would be far too heavy for aircraft use. The physics were straightforward. Effective absorption required either great thickness or very high density, neither compatible with aviation requirements. Moreover, the German scientists argued, if the British had achieved such a breakthrough, they would surely apply it to their bombers, which were suffering catastrophic losses in daylight raids. Why would they waste such technology on fighters, which were already difficult radar targets due to their small size and maneuverability? The logic seemed irrefutable. The explanation had to lie elsewhere, yet the reports kept accumulating. Luftwaffe fighter controllers, who relied on radar data to vector their interceptors toward British formations, were becoming increasingly frustrated. Missions that should have resulted in successful interceptions were failing because the British fighters would disappear from radar at critical moments. Pilots returning from combat reported that they had been surprised by Spitfires that seemed to appear from nowhere, suggesting that the aircraft had approached without being detected by ground radar. Hauptmann Josef Priller, a highly experienced fighter pilot with Jagdgeschwader 26, filed a particularly detailed report in late November after a confused engagement over the Pas de Calais. His swarm had been vectored toward a reported formation of 8 British fighters, but upon arrival at the designated coordinates, they found only 4 aircraft. During the ensuing combat, 2 additional Spitfires appeared unexpectedly, attacking from an advantageous position. Priller wrote, "It is as if certain British aircraft possess the ability to hide from our radar. This gives them a significant tactical advantage. allowing them to position themselves for ambush while our controllers remain unaware of their presence. The report reached Reichsmarshal Hermann Göring, who reacted with characteristic bluster. He declared that German radar was the finest in the world, and that any difficulties were due to operator incompetence or cowardice. The suggestion that the British might possess superior technology was dismissed as defeatist talk. Martini, knowing better than to argue directly with Göring, quietly continued his investigation. In December 1940, an opportunity for direct analysis finally presented itself. A Spitfire from 92 Squadron, coated with Whitmore's paint, was damaged during a sweep over northern France and force-landed near Abbeville. The pilot was captured, but more importantly, the aircraft was recovered largely intact. It was transported to a Luftwaffe technical intelligence facility at Rechlin, where specialists examined every aspect of its construction. The unusual dark gray coating immediately attracted attention. Samples were scraped off and sent to laboratories for analysis. Chemical tests revealed the presence of carbon black, iron oxide, and synthetic rubber, components that could be found in many industrial coatings. The significance of their specific combination and proportions was not immediately apparent. The analysts concluded that it was probably a new type of anti-corrosion paint, or perhaps a visual camouflage experiment. What the German analysts failed to do, because they weren't looking for it, was test the coating's electrical properties. They had no reason to suspect radar absorption, because their own scientists had declared it impractical. The captured Spitfire was catalogued, its unusual paint noted as a curiosity, and the aircraft was eventually scrapped for parts. The samples of Whitmore's formula sat in a laboratory storage cabinet, their true nature unrecognized. This failure of analysis represented a profound intelligence breakdown rooted in doctrinal assumptions. The Germans had convinced themselves that radar-absorbing materials were too heavy for aircraft use. This belief, based on their own research, created a blind spot. They literally could not see what was in front of them because they had already decided it was impossible. Meanwhile, British intelligence, reading German communications through Ultra and other sources, watched this confusion with satisfaction. The Germans were clearly aware that something unusual was happening, but they were flailing for explanations. Some attributed the radar anomalies to new British electronic warfare techniques. Others blamed atmospheric conditions or equipment problems. A few suspected radar-absorbing materials but were overruled by senior scientists who knew such things were impractical. The strategic implications were significant. The Ghost Spitfire program, while still limited in scale, was providing tangible operational advantages. Fighter sweeps over France were achieving higher success rates because German controllers couldn't track all the British aircraft. Bomber escorts were more effective because German fighters, vectored toward the bombers, would miss the escorting Spitfires that had disappeared from radar. And the psychological effect on German radar operators, who were beginning to distrust their equipment, was an unexpected bonus. By early 1941, approximately 150 Spitfires had been coated with the radar-absorbing paint. Production had increased as additional facilities came online, and the manufacturing process was refined. The program was expanding to include other aircraft types, Hurricanes, and experimentally, some Mosquito light bombers. The Air Ministry, initially cautious, was now enthusiastically supporting the effort. But the British also understood that their advantage was temporary. Eventually, the Germans would capture another Ghost aircraft, and this time conduct proper analysis, or their scientists would overcome their doctrinal blindness and recognize what the British had achieved. When that happened, the Germans would develop their own radar-absorbing materials and possibly countermeasures that would negate the British advantage. The race was on to exploit the Ghost Spitfire technology as fully as possible before the secret was revealed. And in the laboratories and factories of Britain, work was already underway on second-generation formulas that would be even more effective and harder for the Germans to copy. In his office at Luftwaffe headquarters, Oberst Martini continued to collect reports of radar anomalies, building a file that grew thicker each week. He remained convinced that the British were doing something clever, even if he couldn't determine exactly what. His requests for more rigorous investigation were repeatedly denied by his superiors, who insisted that German technology was superior and that the problems were merely operational difficulties. It was a failure of imagination that would cost the Luftwaffe dearly in the months ahead. The British, written off by German propaganda as a nation of shopkeepers, had out-innovated the vaunted German scientific establishment. And they had done so not through some dramatic breakthrough, but through the patient, methodical work of a chemist in a Manchester laboratory who understood that sometimes the most powerful weapons are the ones the enemy doesn't believe exist. The crisis that nearly destroyed the Ghost Spitfire program arrived not from enemy action, but from the very success of the technology itself. By March 1941, demand for the radar-absorbing coating had outstripped production capacity by a factor of 3. Fighter Command wanted every Spitfire treated. Bomber Command was requesting the coating for mosquitoes and even heavy bombers. Coastal Command wanted it for anti-submarine patrol aircraft. And the Ministry of Aircraft Production was demanding that the coating be applied to new aircraft coming off production lines, not just retrofitted to existing machines. The production facilities, now numbering 5 across England, Wales, and Scotland, were operating at maximum capacity, running 3 shifts per day, 7 days per week. Workers were exhausted. Equipment was breaking down from constant use, and critically, the supply of key raw materials was becoming dangerously constrained. The carbon black and magnetite could be sourced domestically, but the synthetic rubber binder required chemical precursors that were increasingly difficult to obtain as German U-boats tightened their stranglehold on Atlantic shipping. Jeffrey Whitmore, now holding the title of Director of Special Coatings Development and working from an office in the Ministry of Aircraft Production, faced an impossible dilemma. He could maintain quality and accept that only a fraction of the RAF's aircraft could be treated, or he could attempt to increase production by diluting the formula or relaxing quality standards, risking a product that might fail in operational use. Neither option was acceptable. The situation reached a breaking point in early April when Factory 7 in Huddersfield, still the largest production facility, reported that it would run out of the critical synthetic rubber component within 2 weeks. The supply ship carrying the next shipment of precursor chemicals had been torpedoed in mid-Atlantic. Alternative sources existed, but they were already committed to other war production. Margaret Thornton, now coordinating all production facilities, delivered the grim news to Whitmore. "We can keep the factories running for perhaps 10 more days at current production rates. After that, we'll have to shut down until new supplies arrive, which could be 6 weeks or more." Victory. Whitmore spent a sleepless night in his office, surrounded by chemical formulae and production reports, searching for a solution. The synthetic rubber served 2 purposes in the paint. It provided the binder that held the carbon and magnetite particles together, and it contributed to the coating's flexibility and durability. Could it be replaced? Partially substituted? The original formula had been optimized through months of testing, but perhaps there was room for modification. By dawn, he had a hypothesis. Natural rubber, which was also in short supply but not quite as scarce as the synthetic variety, might work if combined with certain plasticizers to improve its low-temperature flexibility. The electrical properties would be slightly different, but calculations suggested the radar absorption might actually improve at certain frequencies. It was a gamble. There was no time for extensive testing, but it might keep production running while alternative supplies of synthetic rubber were secured. Whitmore called an emergency meeting at Factory 7 for that afternoon. He presented his proposal to a room full of skeptical production engineers and chemists. The objections came immediately. Natural rubber was harder to process, required different mixing procedures, and might not adhere as well to aluminum. Changing the formula mid-production risked creating batches of inconsistent quality, and without proper testing, they could be sending aircraft into combat with coatings that might fail. But the alternative was shutting down production entirely. After 2 hours of heated discussion, a compromise emerged. They would produce a small test batch using the modified formula, conduct accelerated testing over 48 hours, and if the results were acceptable, transition all facilities to the new formula. It was a compressed timeline that violated every principle of proper materials development. But the war didn't allow for proper procedures. The test batch was mixed that evening. Whitmore personally supervised the process, adjusting proportions and additives as the mixture came together. The resulting paint looked slightly different, a bit darker, with a subtle texture variation, but it applied smoothly to test panels. Those panels were immediately subjected to a punishing series of tests: thermal cycling from 40°C to plus 106°C, salt spray exposure, vibration, and impact, and critically, radar reflection measurements using a portable test rig that had been set up in a corner of the factory. Whitmore didn't leave the factory for the next 2 days. He dozed fitfully in his office between test cycles, sustained by endless cups of strong tea and the determination that had carried him through 2 years of relentless work. The factory workers, aware that something critical was happening, maintained production of the standard formula while anxiously awaiting the test results. The news when it came was better than anyone had dared hope. The modified formula performed as well as the original in all respects, and in radar absorption tests, it actually showed a slight improvement at the frequencies used by German Würzburg radars. The natural rubber, combined with the specific plasticizers Whitmore had selected, created a matrix that was more effective at dissipating electromagnetic energy. It was a serendipitous discovery born of desperate necessity. Production transitioned to the new formula within a week. The process required retraining workers and adjusting mixing procedures. The factories managed the change with remarkable efficiency. By late April, paint production was back to full capacity, and the immediate crisis had passed. But the episode had revealed the program's vulnerability to supply chain disruptions, a vulnerability that would need to be addressed. Margaret Thornton attacked the problem with her characteristic vigor. She established strategic reserves of all critical materials, sufficient to maintain production for at least a month if supplies were interrupted. She developed relationships with multiple suppliers for each component, creating redundancy in the supply chain. And she worked with the Ministry of Supply to ensure that the Ghost Spitfire program received priority allocation of scarce materials, a bureaucratic battle that required all her formidable skills of persuasion and, occasionally, intimidation. But even as the production crisis was being resolved, a new challenge emerged from an unexpected quarter: the pilots themselves. Reports began filtering back from operational squadrons that the radar-absorbing coating was degrading more rapidly than standard paint under combat conditions. The high-speed maneuvers, extreme temperature variations, and occasional battle damage were causing the coating to crack, peel, or discolor. Aircraft that had been coated only weeks earlier were showing significant deterioration. The problem was particularly acute on the wing leading edges, where high-speed airflow created erosion, and around gun ports where muzzle blast and hot gases damaged the coating. A Spitfire with a degraded coating was not only less effective against radar, it also looked shabby, which affected pilot morale. Squadron commanders were requesting that aircraft be returned to maintenance facilities for recoating far more frequently than anticipated, creating a logistics burden that threatened to overwhelm the application facilities. Whitmore assembled a team to investigate the durability problem. They visited operational squadrons, examined damaged aircraft, and interviewed pilots and ground crew. The findings were sobering. The coating, optimized for radar absorption and weight, had not been adequately tested for the brutal realities of combat flying. It was a reminder that laboratory success didn't always translate to operational effectiveness. The solution required another round of formula modification. Whitmore added toughening agents to improve abrasion resistance, adjusted the polymer chemistry to enhance flexibility, and developed a clear protective topcoat that could be applied over the radar-absorbing layer to shield it from environmental damage. These changes added slightly to the coating's weight and complexity, but they dramatically improved durability. The improved formula, designated Mark X, entered production in June 1941. Aircraft coated with the new formula showed significantly better resistance to operational wear. The recoating interval extended from weeks to months, easing the logistics burden, and the protective topcoat had an unexpected benefit. It could be tinted to match different camouflage schemes, making the Ghost Spitfires less visually distinctive and thus harder for German intelligence to identify. Throughout these crises, the workers in the production facilities and application centers maintained their dedication. They worked through air raids, material shortages, equipment breakdowns, and the constant pressure of knowing that pilots' lives depended on the quality of their work. The women of Factory 7, still covered in gray carbon dust at the end of each shift, took pride in their contribution to the war effort, even though they couldn't discuss it with their families. One worker, Elsie Morrison, a former weaver from Huddersfield, later recalled, "We didn't know exactly what the paint was for, but we knew it was important." Mr. Whitmore would come through the factory sometimes, checking the batches, and you could see the worry on his face. We all felt the weight of it. Every drum we filled might be the one that saved a pilot's life. So we were careful, even when we were dead tired. We kept the standards high because that's what was needed. Always. By summer 1941, the Ghost Spitfire program had survived its most critical challenges. Production was stable and increasing. The coating's durability had been improved, and the operational advantages were becoming increasingly apparent in combat reports. Fighter Command's loss rates on offensive operations over France had decreased noticeably. Pilots reported that they were achieving surprise more frequently, suggesting that German radar was failing to detect their approach. The program had matured from an experimental concept to an operational capability. More than 300 aircraft were now flying with the radar-absorbing coating, and that number was growing by dozens each week. The Ghost Spitfires had become an integral part of the RAF's offensive capability, a silent advantage that the Germans still didn't fully understand. In his office, Whitmore allowed himself a moment of satisfaction. The crises had been overcome through a combination of scientific ingenuity, industrial determination, and the sheer bloody-mindedness that characterized Britain's war effort. The paint that had started as a theoretical possibility in a laboratory was now a proven weapon, protecting British pilots and confounding German defenses. But he knew the battle wasn't over. The Germans were resourceful and would eventually develop countermeasures. The next phase would require staying ahead of their efforts, improving the coating, developing new variants, and finding additional applications. The race between innovation and counter-innovation would continue as long as the war lasted, and Whitmore was determined that Britain would stay ahead. By autumn 1941, the cumulative effect of the Ghost Spitfire program had fundamentally altered the tactical balance over occupied Europe. German radar operators, once confident in their ability to track and vector interceptors toward British formations, now faced a situation that bordered on the surreal. Formations that should have been clearly visible on their screens appeared as fragmentary, intermittent contacts that faded in and out unpredictably. Fighter controllers, relying on this degraded information, were vectoring their pilots toward empty sky or into disadvantageous positions where the British held the element of surprise. The operational statistics told a compelling story. RAF Fighter Command's offensive sweeps over France, which had suffered prohibitive losses in early 1941, were now achieving kill ratios that favored the British by margins of 2-to-1 or better. Bomber escorts were more effective, with German interceptors frequently failing to locate the escorting fighters until after they had already engaged. And most tellingly, German fighter pilots were reporting a dramatic increase in surprise attacks, Spitfires appearing from nowhere to bounce formations that believed themselves safely positioned. Oberst Wolfgang Martini, still investigating the radar anomalies, had by now accumulated a file of reports that could no longer be dismissed as equipment malfunction or operator error. The pattern was too consistent, too widespread. In November 1941, he finally obtained authorization to conduct a comprehensive technical investigation. A team of scientists and engineers from Telefunken was dispatched to radar stations along the French coast with instructions to determine definitively what was causing the tracking difficulties. The investigation took 3 weeks and involved careful analysis of radar returns from known British formations, comparison of different radar systems, and extensive equipment testing. The conclusion, delivered to Martini in early December, was both enlightening and deeply troubling. The radar systems were functioning perfectly. The problem was not with German technology, but with the targets themselves. Certain British aircraft, estimated at 20–30% of the fighters encountered, exhibited radar cross-sections that were dramatically reduced compared to standard aircraft. The reduction was too significant and too consistent to be explained by natural variations or atmospheric effects. The report landed on Martini's desk on December 5, 1941. 2 days later, the Japanese attacked Pearl Harbor, and Germany declared war on the United States. In the chaos of these world-changing events, Martini's report might have been overlooked, but he ensured it reached the highest levels of the Luftwaffe command. On December 15th, he briefed General Feldmarschall Erhard Milch, State Secretary of Aviation, on the findings. Milch's reaction was one of stunned disbelief, followed by anger. "You're telling me the British have developed radar-absorbing materials, but our own scientists said this was impossible." Martini, choosing his words carefully, explained that the German research had concluded such materials would be too heavy for practical use. But the British had apparently solved that problem. Milch immediately ordered a crash program to develop German equivalents and to devise countermeasures. The damage was already done. For more than a year, the British had operated with a significant technological advantage, while the Germans remained blind to its existence. The psychological impact on the Luftwaffe was profound. Pilots who had trusted their ground controllers to provide accurate information about enemy positions now questioned whether they were being given complete intelligence. Radar operators, who had been blamed for tracking failures, felt vindicated, but also demoralized by the realization that they had been fighting an invisible enemy. German fighter ace Adolf Galland, commander of Jagdgeschwader 26, wrote in his diary, "We have been fighting with one hand tied behind our backs, and we didn't even know it. The British Spitfires we thought we were tracking were only part of the force. Others were approaching undetected, positioning themselves for attack, while our controllers assured us the sky was clear. How many pilots have we lost because we didn't know the enemy could hide from our radar? The thought is maddening." The German response, when it finally came, was characteristically thorough, but ultimately too late. Luftwaffe Technical Intelligence launched an intensive effort to obtain samples of the British coding. Pilots were offered rewards for forcing coded British aircraft to land in occupied territory. Agents in Britain were tasked with gathering information about production facilities. And German scientists began their own research into radar-absorbing materials, now knowing that the problem was solvable. In January 1942, a Ghost Spitfire from 611 Squadron was shot down over Belgium and crashed in a manner that left much of the fuselage intact. The wreckage was immediately secured and transported to Rechlin for analysis. This time, the German scientists knew what to look for. Samples of the coating were subjected to extensive electrical testing, revealing its radar-absorbing properties. Chemical analysis identified the key components: carbon black, magnetite, and a rubber binder. The German scientific community reacted with a mixture of admiration and chagrin. Dr. Hans Plendl, who had suggested the possibility of radar-absorbing materials a year earlier, only to be dismissed, was vindicated, but took no pleasure in it. "The British have demonstrated that our assumptions were wrong," he told colleagues. "They found a way to make the material light enough for aircraft use. We should have pursued this research more aggressively. Now we are playing catch-up." German efforts to develop their own radar-absorbing coatings began immediately, but they faced the same challenges that had confronted Whitmore 2 years earlier: finding the right combination of materials, optimizing the formula for weight and effectiveness, and establishing production facilities. The Germans had the advantage of being able to analyze the British coating, but they lacked the years of development and refinement that had gone into perfecting it. Moreover, Germany's industrial capacity was increasingly strained by the demands of fighting on multiple fronts. Raw materials were scarce. Skilled chemists and engineers were needed for countless other projects, and the Luftwaffe's priorities were shifting toward defensive operations as Allied bombing campaigns intensified. The radar-absorbing coating program, while recognized as important, competed with dozens of other urgent requirements. By mid-1942, the Germans had produced experimental batches of their own radar-absorbing paint, designated Schornsteinfeger, chimney sweep, for its dark color. Testing showed it was effective, though not quite as good as the British formula. But production remained limited, and application was restricted to a small number of night fighters operating in the defense of the Reich. The widespread deployment that might have negated the British advantage never materialized. Meanwhile, the British continued to refine and expand their program. Whitmore's team developed improved formulas with better absorption characteristics across a wider range of radar frequencies. Production capacity increased to the point where not just fighters, but also mosquito bombers and even some heavy bombers could be coated, and the application process was streamlined, reducing the time required to treat each aircraft. The strategic impact extended beyond mere tactical advantages in air combat. The Ghost Spitfire program had forced the Germans to divert resources to investigating and countering a threat they had initially dismissed as impossible. It had undermined confidence in German radar systems and the intelligence they provided, and it had demonstrated that British scientific and industrial capabilities were more formidable than German propaganda had suggested. Perhaps most significantly, it had shown that technological surprise could be achieved and maintained even in the middle of a total war where both sides were desperately seeking any advantage. The British had identified a vulnerability in German defenses, developed a solution, and exploited it for more than a year before the enemy fully understood what was happening. It was a masterclass in operational security and technological innovation. In the radar stations along the French coast, German operators continued their work with the knowledge that some of the British aircraft they were trying to track were deliberately designed to evade detection. They adjusted their procedures, increased their vigilance, and learned to interpret the fragmentary contacts that might indicate Ghost Spitfires. But the fundamental advantage remained with the British, the ability to approach undetected, to achieve surprise, and to dictate the terms of engagement. Flight Lieutenant David Crook, still flying his Undertaker's Special, wrote in his diary in March 1942, "Had a wizard show over St. Omer today. We bounced a gaggle of 109s that never saw us coming. Their controller must have been asleep, or perhaps he simply couldn't see us on his radar. Whatever the reason, we had them cold. 4 confirmed kills for the loss of none. Days like this make one feel that we're finally getting the upper hand." What Crook still didn't know was that his aircraft's unusual paint was the reason the German controller had been asleep. The Ghost Spitfires had given him and hundreds of other RAF pilots an invisible shield that protected them from the enemy's electronic eyes. And that advantage, born in a Manchester laboratory and produced in factories across Britain by workers who never knew the full significance of their labor, had helped turn the tide of the air war over Europe. The Ghost Spitfire program officially ended in May 1945 as the war in Europe concluded and the urgent need for radar-absorbing coatings diminished. By that time, more than 2,000 British aircraft had been treated with Whitmore's formula or its successors, and the technology had evolved through multiple generations of improvement. The final Mark V formula, introduced in late 1944, was effective against the full spectrum of German radar frequencies and had been applied to aircraft ranging from Spitfires to Lancasters to the new Meteor jet fighters. The program's contribution to Allied victory, while difficult to quantify precisely, was substantial. Post-war analysis by RAF Operational Research estimated that the radar-absorbing coating had reduced aircraft losses on offensive operations over occupied Europe by approximately 15 to 20% compared to what would have been expected without the technology. In human terms, this translated to hundreds of pilots' lives saved and dozens of successful missions that might otherwise have failed. But the true legacy of the Ghost Spitfire program extended far beyond its immediate tactical impact. It had pioneered an entirely new field of military technology, stealth. The principles that Jeffrey Whitmore had discovered, that radar reflections could be reduced through careful materials engineering, would form the foundation for decades of subsequent research. The concept of designing aircraft to evade detection, rather than simply to fly faster or higher, had been proven in combat. In the immediate post-war period, the technology remained highly classified. The British government, recognizing its potential value, maintained strict secrecy around the program's details. Whitmore and his team were quietly honored. He received an OBE in the 1946 New Year honors, with a citation vaguely referring to services to aviation research, but the specifics of their work remained unknown to the public. The production facilities were gradually shut down as the need for the coating disappeared. Factory 7 in Huddersfield returned to civilian chemical production, manufacturing dyes, and industrial coatings. The workers dispersed to other jobs, carrying with them the knowledge that they had contributed to something important, even if they never learned exactly what. Elsie Morrison, the former weaver, returned to the textile industry and lived to the age of 94, never speaking publicly about her wartime work until the program was finally declassified in 1975. Jeffrey Whitmore returned to Imperial Chemical Industries, where he led research into advanced materials for the next 2 decades. He continued to consult with the Ministry of Defense on classified projects, applying the lessons learned from the radar-absorbing paint to new challenges. In private conversations with colleagues, he would occasionally reflect on the war years with a mixture of pride and humility. "We did what was needed," he would say. "Nothing more, nothing less. That's what everyone did in those days." Margaret Thornton, whose organizational genius had been crucial to the program's success, joined the newly formed National Health Service in 1948, where she applied her formidable skills to establishing supply chains for medical equipment and pharmaceuticals. She rarely spoke of her wartime work, but those who knew her recognized the same determination and efficiency that had kept the paint factories running through crises and setbacks. The technical knowledge gained from the program did not remain dormant. In the 1950s, as the Cold War intensified and radar technology advanced, British and American researchers revisited the principles of radar absorption. The V-bomber force, Britain's nuclear deterrent, incorporated radar-absorbing materials in critical areas. Research into stealth technology accelerated, leading eventually to aircraft like the American F-117 and B-2, which took the concept to its logical conclusion. Aircraft designed from the outset to be nearly invisible to radar. The German scientists, who had finally understood what the British had achieved, also contributed to this post-war development. Many were recruited by the Americans or Soviets and brought their knowledge of radar and countermeasures to their new employers. Dr. Hans Plendl, who had recognized the possibility of radar-absorbing materials, worked on radar systems in the United States after the war and occasionally corresponded with Whitmore. Two men sharing a professional respect transcended their wartime opposition. The declassification of the Ghost Spitfire program in 1975 caused a minor sensation in aviation and military history circles. Historians who had studied the air war over Europe suddenly had an explanation for statistical anomalies they had noted. The unexpectedly favorable loss rates for certain RAF squadrons, the German reports of radar difficulties, the references in pilot memoirs to aircraft with unusual paint schemes. The pieces of a puzzle that had been scattered across decades of records suddenly fit together. David Crook, who had survived the war and become a commercial pilot, learned for the first time why his Undertaker's Special had seemed to bring him luck. In an interview given shortly before his death in 1978, he reflected, "All those years, I thought it was just paint. I never imagined it was making us invisible to German radar." It makes you think about all the times we came back safely when we might not have. We owed our lives to people whose names we never knew. The chemists, the factory workers, the engineers. That's the real story of the war, isn't it? Not just the chaps in the cockpits, but everyone who contributed. The technical papers that Whitmore and his team had produced during the war, once declassified, became foundational texts in the field of radar-absorbing materials. Universities incorporated them into engineering curricula. Defense contractors studied them for insights into materials design. And a new generation of scientists built upon the work, developing ever more sophisticated approaches to stealth technology. In 1982, a small ceremony was held at the Imperial War Museum to commemorate the Ghost Spitfire program. Jeffrey Whitmore, then 76 years old, attended along with several of the surviving team members and factory workers. A Spitfire painted in the distinctive dark gray of the radar-absorbing coating was placed on display, with a plaque explaining its significance. Whitmore's brief speech captured the spirit of the program. We were asked to solve a problem that seemed impossible. We didn't have much time, much money, or much encouragement, but we had determination, and we had each other. That turned out to be enough. The legacy of the Ghost Spitfire program resonates in modern military aviation. Every stealth aircraft flying today, from the F-35 to the latest unmanned combat vehicles, incorporates descendants of the principles that Whitmore discovered in his Manchester laboratory. The idea that aircraft can be designed to evade detection rather than simply to outperform the enemy has become fundamental to air combat doctrine. But perhaps the most important legacy is less tangible, the demonstration that innovation can emerge from unexpected places and that technological advantage can be achieved through persistence, creativity, and the willingness to challenge conventional wisdom. The German scientists who declared radar-absorbing materials impractical were not fools. They were working from reasonable assumptions based on the knowledge available to them. Whitmore succeeded because he questioned those assumptions and was willing to try approaches that others had dismissed. The story of the Ghost Spitfires also exemplifies the British character during the war years: the quiet determination, the refusal to accept defeat, the ability to innovate under pressure, and the collective effort that united people from all walks of life in common purpose. From the chemist in his laboratory, to the workers in the factories, to the pilots in the cockpits, each played a role in creating an advantage that helped turn the tide of the air war. In the decades since the war, as the details of countless secret programs have been revealed, the Ghost Spitfire program stands out as a remarkable achievement. It was not the most dramatic or the most celebrated contribution to victory. That honor belongs to efforts like the codebreakers at Bletchley Park or the scientists who developed radar itself. But it was significant nonetheless, a quiet triumph of ingenuity over adversity, of persistence over skepticism, and of British determination over German technological confidence. Jeffrey Whitmore passed away in 1989, having lived to see his wartime work recognized and appreciated. His obituary in the Times, while noting his distinguished career in industrial chemistry, gave particular prominence to his role in developing the radar-absorbing paint. The final paragraph captured his contribution succinctly. In the dark days of 1940, when Britain stood alone, Jeffrey Whitmore gave the RAF a weapon that the enemy could not see. In doing so, he helped ensure that the nation would survive to see victory. It was, in every sense, a quiet triumph, and all the more remarkable for it. The Ghost Spitfires themselves, those aircraft that flew through hostile skies cloaked in Whitmore's invisible shield, have long since been retired or scrapped. But their legacy endures in the museums where examples are preserved, in the technical literature that traces the evolution of stealth technology, and in the memory of those who flew them and those who made them possible. They represent a chapter in the history of warfare when innovation and determination combined to create an advantage that helped free a continent from tyranny. And in that achievement, there is a lesson that transcends the specifics of radar and paint and aerial combat. But the impossible is often merely the difficult in disguise, waiting for someone with the vision and persistence to make it real. If you've enjoyed this remarkable tale of British ingenuity and determination during the Second World War, please do subscribe to our channel and share your thoughts in the comments below. What other untold stories of wartime innovation would you like us to explore? From the boffins at Bletchley Park to the engineers in shadow factories across Britain, Countless unsung heroes contributed to victory in ways that remained secret for decades. Let us know which stories you'd like to hear next, and don't forget to hit the notification bell so you never miss our deep dives into history's most fascinating chapters.